Welcome everyone to this presentation of Total Lab Automation. Disclaimers: all the images shown in this presentation are purely for illustrative purposes and any resemblance to people known is purely coincidental and unintentional. Now, I worked in Medanta, which has a good state-of-art automation in the biochemistry section, and currently I am with the Amrita Hospitals, which has got a lab that one just needs to see to believe. Full state of automation we have in this lab. So when we are talking about working in the lab, all of us will know that our work is increasing exponentially and the expectations of our clientele, be it the doctor or the patient, is progressively increasing. The clinicians want the report even before the sample has been sent, and because the patients are now paying money for the test and they're viewing lab services more as commodities, from a request it's turned to a kind of a demand. Most of us in the setup that we are working right now would actually be feeling that we are working running in a bullock cart. The demands are more and we're not able to catch up with it. That's when the company vendors come up to us and sell us the concept of total lab automation and say, if you have all the automation features, it'll be like this Ferrari car. You can simply zoom through it. Get excited? Buy this car, step in this car, and the moment I press the accelerator, bang. And then I get out of the car and say, this car really got us into trouble. At least the bullock cart didn't get us into a problem. I think many of us who have tried and experimenting on automation would be in this stage. So the question arises here, is it a problem with the car? Is the bullock cart safe? Or is there something in between? Give this car to Formula 1 racers like Michael Schumacher or Ayrton Senna, and they will take this car at 200-250 kilometers and say it works like a bird. So the problem is not with the car. The problem is with us in not able to drive it to that potential. So the aim of this presentation is to highlight the concepts of total lab automation, which could make a bullock cart driver to a Formula 1 driver. Let's quickly understand the evolution of automation, right from the days when we had the Levy-bound comparator to the days when we had mouth pipetting and this colorimeter. We progressed on to semi-auto analyzers and fully automatic analyzers, and then now we have this multi-systems, total lab automation. What does total lab automation comprise? First, we need to study the processes in the lab, see what are the processes that are repetitive in nature, and those are the processes that can be outsourced for automation. There are two aspects which can be automated, the hand and the brain. Chutti is an example where both hands and brain were automated. Let's talk about automation of the hand. This is probably the part of the automation that most of us are eager about and excited to know. Well, the manual processes in the lab include decapping the sample, centrifuging it, assigning it to the analyzers which have the reagents in it. Now here we should keep in mind what was the workload assigned to that analyzer, and also we need to know the QC status of that analyzer. After the sample has been run, in case the samples have to be run in dilution, in case there are some add-on tests on that sample, we need to retrieve the sample and do the test. And once everything is done, the sample needs to be recapped and stored, later disposed. For this, in automation, we have a lot of options. We have the bulk sample loader, where you just simply drop in all the samples as if you drop trash. It automatically aligns it and puts it into the conveyor belt. Then we have an online centrifuge. The sample comes to the centrifuge, once the numbers are achieved, once the time period is achieved, the samples get centrifuged for the given RPM, for the given duration, and it progresses on. Here again, we put it in the bulk loader, it comes to the online centrifuge, gets centrifuged. Then we have an online decapper unit. It removes the cap so that now the analyzers will be able to aspirate the samples out of it. There are certain analyzers which have a cap piercing technology where the probe can go through the cap and collect the sample. Then we have these conveyor belts where the sample travels from the time it is being bulk loaded to the time it reaches the analyzer for testing. Most commonly we have the conveyor belts There are systems which we got magnetic levitation and the samples zip through the track. And then there are certain other instruments which have got mobile sample carts. In that there's no conveyor belt, but each sample passes in a separate cart and goes to the analyzer. Now these are just various techniques in which the samples can be transported from the time the sample has been loaded in the bulk loader to the time it reaches the analyzer for testing. In the sample processing unit, we have a place where we can load the sample. We can have a criteria to sort the samples for secondary offline purposes. We have a buffering area, that is the samples after being processed and still not yet resulted can be parked in this buffering area. And we have a sample storage, right, where the samples can be stored for later purpose. After the test has been performed, the samples get sealed and then are kept in the sample storage area. Effectively, if you play the game correctly, one does not need to touch the samples, a no-touch technique. But then using a no-touch technique comes with a price. Depends upon how much you're ready to invest in it. The bulk loader, the online centrifuge, the track systems, the sample recapper, online storage, each of them come with a particular price. So depending upon what is the state of your lab, what is your workload, you can plan and choose all these options on an add-on basis. More important than these automated systems is the concept of lean study. Now what do we mean by concept of lean study? What normally is done is when we take this lean study, we do this spaghetti diagram wherein we trace a sample as to how did the sample traverse in the lab. We have to mark down how many times the technicians had to touch the sample, where all did he walk to put the sample till the time the result was generated. And then we analyze this as to how is the workflow going. Is there a need to streamline the process? Is there a need to adjust the layout of the lab in such a way that the sample flow becomes optimal? This is something that needs to be done. What most of the labs make a mistake is they do the spaghetti diagram and they do a lean management once thoroughly and they think it is done. It would be good for some time until you get some new equipments, and then again the sample flow workflow process may have got interrupted. So it makes sense that once a year a spaghetti diagram be done so that you know that your lab is optimally oriented for most efficient output. This was about automation of the hands. Automating of the brain is something that nobody talks much about, but this is where I feel that a lot of work can be done and does not cost too much. When we talk about automating the brain, the most common term that we would be hearing about is a middleware. What is a middleware? Ideally, in a system, in a hospital, if these were the wards and these were the analyzers and each ward had to talk to the analyzer, then you can imagine the number of lines and the number of crisscrossing of the wirings that will occur. And this crisscross creates maximum potential for breakdowns. A middleware is a computer. Effectively, a middleware is a computer which is in between the end user and the analyzers. All the end users communicate to the middleware. All the analyzers communicate to the middleware, and it is through the middleware that the data can be transferred from any analyzer to the end user, or any information from the end user can go to the analyzer, simplifying the wiring. It is just a computer and one needs to invest on it. The major thing in the lab that we have about is releasing results within the turnaround time and addressing priority samples. Now, this is what I had created in my lab, where I have a list of all the samples. The urgent samples come first and the routine samples come later. This is adjusted in the ascending order of the time that the sample was received, so that the first come sample, the urgent samples, get prioritized and released. Another thing that happens in the lab is that the TAT monitoring is usually not known to the technicians in the bench when they are working on a daily basis. As a result of it, at the end of the month, they get a figure that their TAT was so good or so bad when they are not in a position to do anything. We created a simple graph that showed the current TAT of the day. This visual representation to the technicians told them when they were doing good, when they were doing bad, and there was a positive feedback, and they ensured that the TAT was also always consistent. Now in this result, we find that on a particular date, the TAT was bad. This is the time as a manager, I need to check up what happened on that day, what are the factors that led to the TAT turnaround time being out, and what are the measures that we can do to ensure that it doesn't repeat again. Another word which I call always is a concept of number blindness. When we are releasing numerical reports, be it in the biochemistry or the hematology, beyond a particular time, there are numbers, we are seeing the numbers, but our brain fails to really react to differences. Maybe the first 10 results we are looking at it very cautiously. Over a period of time, it becomes a monotonous drill. We are seeing the numbers, but our brain is not registering it, and this is what I call number blindness. If there was a comment on the report saying that this particular report is showing a gross difference, okay, my brain gets tuned to this flag, looks more in details for this, and then analyzes the report. So this is where using delta checks to identify samples which are beyond a acceptable range and flagging it makes reporting better. Now what are delta checks? Delta checks, we can set rules by parameters. We can, for a single parameter, we can select multiple rules. For example, in creatinine, when the creatinine level is less than 1.5, a 0.2 milligram per deciliter difference of creatinine level should trigger out a delta check flag. However, if the patient is having a creatinine of 6, then even a 2 milligram per deciliter of creatinine would not really affect me too much. So the rules of delta check should be, there should be multiple rules for parameters. It can be set at various ranges. You can use absolute values, that is a difference of 1 milligram per deciliter, a milligram of a difference of 0.5 milliequivalents per liter, that kind of absolute values. Or you can use a value that a 10% difference from the previous value should be considered as abnormal. So we can mention those kind of rules. The rules must be clear and ambiguous. Like you say, if the value is between 0 to 2, do X. If the value is between 3 to 5, you do Y. Then if the value is between 2.5, the computer doesn't have an instruction to what to do. If you say between 0 to 2, do X, between 2 to 4, you do Y, at the level of 2, the computer gets confused whether I should use the previous rule or the second rule. So your rules should be very clear and unambiguous. Now, when these delta checks get flagged out, you can look at it carefully, analyze those samples, and then react accordingly. Remember, one size does not fit all. You can't use a delta check rule of one hospital and blindly apply it in all the other hospitals. Every hospital has got its own dynamics. For example, if I am a pediatric hospital, swinging of a glucose of 250, 300 would be grossly abnormal to me. But if I'm a diabetic center, a glucose of 200 is a routine run-of-the-mill results. So you can't use the same criteria everywhere. We need to titrate it to our hospital in such a way that there is a 80-20 ratio or a 70-30 ratio, that 70% of the samples don't get flagged and 30% of the samples get flagged. If your rules are such that every sample is getting flagged, then probably your rules are too stringent. If your rules are such that many samples don't get flagged, then your rules are too lenient. You need to titrate it. Now, how does delta check actually help? When we are running against the pressure of time for TAT, it is impossible to do a research as to why these results were out and what was the justification for it. But what I would do is, after I release the report, I take a report of all the samples which had a delta check flag and then individually ask the doctors about why the flagging occurred. By clicking this button, I get the entire profile of the patient. I know what all has happened to the patient, and I'm in a position of authority to talk to the doctor and actually discuss whether the difference, like here, there was a sudden jump in the bilirubin from 0.9 to 3.1. So I can ask the doctor as to what has happened to him, why has the levels chosen increased, and probably I could also contribute a little bit into further aspect of management of this patient. Auto verification is something which is very big, being talked quite high when it comes to lab automation. The way the IT sells it is auto verification can identify all the normal reports and release it so that you just focus your attention on only those samples that bind. The way the management sees it, most of the work is being done by the computer, so we can go ahead and release and get and fire off some people and be optimal on the manpower. The way I see it is, as long as everything goes fine, it's okay. When something goes wrong, I'm the scapegoat, and the whole system, the management, the IT, everybody turns back to me and says, you set the rules, it's your problem, now you manage the mess. So if it is good, they are good. If it is bad, I am bad, and that keeps me very vulnerable. When organization cuts cost by cutting manpower, they progressively return the manpower till the system collapses, and then they promptly turn back to you and say you are incompetent. Now I'll give you an example of what I think about Delta Check. If you are a hypertensive patient and you've paid 5,000 rupees to go to the top cardiologist for a consult, and his receptionist in the OPD takes a blood pressure, finds that it is normal, and says you're doing very good, now carry on with the same medication and come back after 2 months. Your 5,000 rupees is gone. Would you take it? Probably the cardiologist, when you meet him, would also have done the same thing and said the same thing. But you feel cheated that you paid 5,000 rupees to see a cardiologist and the cardiologist didn't see you. But then when you talk about auto verification, well, that's a different story altogether. Automation should be viewed as a source to improve your productivity. Now that is something which we need to understand. Automation is not a source for cost cutting. See, in the lab, I have some basic processes, sample processing from the centrifugation to the assigning of the analyzer to generation of the results to doing it in dilution and releasing requires some manpower. Whether I handle one sample or whether I handle 1,000 samples, the documentation and the processes don't change. Manpower is the function of the processes and not the sample load. This is something that we all need to understand very clearly. My take on automation is, if you're looking at it for reducing manpower, that's a failure model. But if you say that, look, with the existing manpower and automation, previously I could handle 20 samples, now I'm in a position to handle 200 samples, and then I send my marketing team to get me the remaining 180 samples. That is the time automation is going to work. Now look at this cockpit of A320. It's a beautiful system. It works by the fly-by-wire technology. You know, when the plane is flying, if one engine is shut off, the computers will automatically take over and guide the plane properly. So much so that it can even automatically land the plane. But then you will see a pilot. You not only see a pilot, you'll also see a co-pilot. Two people doing a job which the plane is as such able to do. Why? Because we have 300, 400 passengers on the flight. If anything goes wrong, all of them will die. That's a big problem. So we need the security, safety measure. This is apparent. But when we cut off manpower, we are making our results vulnerable and the patients who are going to be treated vulnerable, and we are creating more patient harm than possibly what could happen by firing these two pilots. But since it's not apparent, it is not appreciated. The major question that keeps coming on is, will the machines take over mankind? There are a lot of movies that have been made on this. Are we going to lose our jobs to this computer? because what I can do, the computer can do better than me? Well, we need to understand that artificial intelligence automation is like a bulldozer. It is coming. Accept it, be prepared for it. If you tend to fight it, it will just roll you down into a piece of paper and carry on. What we need to be doing about it is, we should be prepared for it. We should be ahead of it. We should be the masters, and we should be driving in artificial intelligence to harness it to our benefit. As one of my mentors, General Kavita Sahai, said, AI cannot take the job of pathologists, but pathologists who do not adopt AI will soon get replaced. Another set of people who are very dangerous when it comes to automation are these rocket sinks. They go and tell the clinicians that there are these point of care testing devices. These can be used for doing the test. You don't need to send the sample to the lab. You can do it in your OPD. The amount of vagaries that happen in these point of care testing device is tremendous, and it actually causes more damage than good to the patients. There's another talk on numbers lie, be aware and beware, in which I'll be addressing this issue. My take-home message in this entire presentation is, when we are going for automation, we're supposed to be very clear as to what are we looking for. If we are looking for automation as a source to reduce manpower, that's a failure model. Neither will you get your derived benefit, nor your technicians will adopt the automation, and they'll keep plugging holes because they are threatened. Today, when I talk about automation, I'm not threatened. It's my technicians who are threatened, and so I happily adopt it. But remember, as long as your technicians are threatened about their job, they are not going to let automation come in. However, if you look at automation as a way to increase your productivity without firing the manpower, but increasing your workload so that you can process more samples, that would be the true use of automation. That's when your technicians will also adopt it, and that's when you'll be able to harness the potentials of automation. One has to be very clear about this. Thank you very much.